All right, so we're gonna get going. We're just doing the problems that I kind of chose in here. We are not going to do free response. I believe you have 11 examples. I honestly can't make up any more. Those are the big situations. So take a look at those, review those, study those. Please read through them. If you don't quite remember them, then try to read the problem and not look at the answer, and then see if you kind of remember how that one went down. So we had 7, I think, from large group, and then another 4 from Friday last week. Quickly, I got a fun little toy, an infrared, which links to this lab, or this chapter, an infrared thermometer. So those of you that didn't believe when you touch the top of your desk and touch the leg of the desk that they're at the same temp, you can definitely use this. And you can either pinpoint it with a dot, or you can just do an overall zone reading. For example, my shirt is 86 degrees, but my arm is 91.8. Holy cow. So, and that's just the surface temp. So we're going to use this sometimes in labs this year to see if something's hot. Or if you ever are unsure to touch it, you can use that gun. All right, away we go. First one, I just thought this was appropriate. Place everything. So can you place, I'm sorry, on the board it's hard to read, but on the sheet it's very visible. Place everything. So you got red, radio, UV, violet, gamma, visible, yellow, IR, blue, micro, and X-ray. If you haven't already done it, can you do that? You should know every single location of all of that. So I'm just going to give you a minute. I'm telling you now, this sheet is not enough space for some of this stuff, so either you're going to do it on the back, or you might need a piece of loose leaf. I didn't design this to be able to write on here because it would have taken up way too much space in general for that to happen. So I'm going to pause it for a sec, finish up, and then hit play. All right, so I hope this is what you put. You should be able to do this without looking at anything. If you're confused on one side or the other, it does help with the colors. So violet's furthest to the left, so that would be ultraviolet. Red is furthest to the right, so that's infrared. What's the time here? Radio. Then you got blue and what do I have? Yellow? Approximately. Not need to know blue and yellow wavelengths, just violet to red. Okay, so there's not a lot to be said about that, just understand it. I do not need you to know values. Always, just last comment, if you're ever unsure, once in a while I've seen a dirty trick where they put an electromagnetic spectrum and then it's not based on wavelengths. There always has to be some sort of a unit. So just double check it. Make sure, oh, that's based on wavelength or that's based on meters. Okay. All right, so calculate the frequency of blue light of wavelength of 450 nanometers. So it tells you that you need to understand that you need to be able to show an equation. All the hidden points are, do you have the equation and the relationship? Do you have all your numbers in the units? And if you have your final answer. If you want ever to do this with your orange sheets, be my guest. You get to use that on the test tomorrow anyway. It's not a bad idea. As always, never write on it. If it ever has any writing on it, I take it, it's gone. You don't get a new one. It's gone. That's it. Not worth it ever. So, give it a shot. I'm going to pause it for a sec. I hope this is what we do. I would love you to do it the way that, to be honest, the way that I do it. Like, I set it up well. I was taught, I thought, very well by all my instructors to reorganize. If you're all like, no, I'm just going to cross multiply and divide, which it's going to look like that. Actually, usually it's like this. It's great, but you still got to plug it all in. So you might as well solve for the actual one. Plug in the numbers. Anybody with the actual sheet out, is it 3.0 or are they using like 2.98 or 2.99? 2.998. You can do 3.0. If you want to use that one because you feel comfortable because it's in front of you, awesome. But just understand a lot of times it is rounded up. All right, here's the thing. 450, I guess, is this okay? No, 450 times 10, -9, and then that's meters. If you're uncomfortable with that, that's not how you write scientific notation. Great. then you need to do the extra brain power to understand that that's 4.5 times 10 to the negative 7th. And then right there, you're like, wait, negative 7th or negative 11th? Which one? Right there, it's defeating the purpose of what we're doing. Just put negative 9. That's my n. Right? That's my nano. That's perfect. Shoot, I don't have it. Of course, I don't bring a calculator. Because it's a frequency, I'm going to guess it's something to the 14th. Because it's a color. I could be wrong. And to get the full point, you need the right unit, and it may not tell you it. Options. What does someone have written? Hertz. What's something else? Inverted seconds, which it could look like that, right? Or like that. Either one. Please don't do more than one unit. It's wrong. Well, no, I was putting all the options. No, 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 no. You don't put all the options. You put one, and you're done. So that's what it would be. Can you do it? I mean, I'm going to have some that just, can you execute it? There will be some that are very straightforward and pretty easy. Ones that are a little more complicated, like this one. The wording can be confusing. It says it takes 6.72 times 10 to the negative 18 joules of energy to remove an electron from an unknown atom. What is the maximum wavelength of light that can do this? What? Okay, so this then deals with energy, right? This deals with wavelength. So can you come up with a relationship of energy and wavelength to solve for this? Is there something that you know that we've used? Give it a shot. No problem. I'll do this first. Okay, that's fantastic. But what equation do I need to actually write as? Like if I really want to commit to solving for wavelength. How do I do that? What does that look like? Anybody? What is wavelength equals? HC over E. Right, don't need to switch. It's on the top and the left. To bring it to the other side, it has to go on the bottom. If it's on the bottom on one side, it can go on the top on the other side. Multiply and divide. So, it should look just like this. If you don't have what I'm writing, it's not enough. No matter how you're interpreting this, like, well, yeah, I'm not going to do that part. Then you will lose points. I got approximately, correct me if I'm wrong, because this calculator is about to die. Is that right? What would that be in that? Yeah.
So like I did the equation that I said, but I got the same answer, right?
It is. I'm just trying to push you more and more to try to rearrange. That's all. What is that in nanometers? Anybody know? It's a good follow-up question. What is this in nanometers? How would I write that? So nanometers is times 10 to the negative 9th. So I guess my question is to you. Is it 29.6 nanometers? Or is it 0.296 nanometers? You're like, wait, what are you talking about? So if I want to convert this to times 10 to the negative 9th meters, where does that decimal go? Seth, is it 29.6 or 0.296? If you're ever unsure, first you could break it down and go all the way back 8. Think of it this way. Break it down, go back 8 to the left, right? And then would you go 9 back to the right? Okay. Another thing, when I say 700 nanometers, that's 7 times 10 to the negative 7. So it moves that way. So yes, it is 29.6. I'm just manipulating numbers, that's all. But it's something that can happen, and you might need to know. Okay. All right, now let's get a little more complicated. So number 4, you're going to want to probably collaborate with someone potentially. There are 4 questions here. A carbon-oxygen double bond in a certain organic molecule absorbs radiation that has a frequency of 6.0 times 10 to the 13. To what region of the spectrum does this radiation belong? So A, someone, what am I doing? It doesn't say anything else. This is where your extra knowledge and being comfortable with the topic has to kind of kick in. I'm just asking what region. So what do I do? Solve for wavelength. Isn't that the spectrum? It will be on your test somewhere if I ask this. It won't be like, oh my gosh, I need to know. No, you would have a spectrum somewhere then. I have to have one there. I'm not going to not have it. So I'm going to solve for wavelength. So, oh shoot, I didn't read this very well. Awesome. So A and B are all linked together. Lame. If you're thinking right now, like, how the heck would I know A then? You would have to solve for wavelength. With at least the information we have. So do that first. We'll talk about letter C in a minute. So I'll give you about a minute. Try to get that done. If you can, try not to look at it once. Can you figure this out without looking? Or take a shot. You should be able to guess within one. Like, could you guess? Maybe you've already looked. But if you haven't, I try to guess. After you get the answer, obviously. Without looking, although it's right above your sheet, it's really hard not to see. What's it good? If you haven't looked, if you looked, don't answer. Anybody who hasn't looked, you want to give it a stab and think what you might think it is? Now you may have already checked. Is that visible light? What is visible light? Times 10 to the -7. So, which way would that go? To the right or the left on my spectrum? 10 to -6. Go to the right. It's bigger actually, even though our brains are going to tell you it's smaller. It's -6. So what's directly to the right of visible light? Infrared. So that should be infrared. I mean, I'm not looking at it right now. I'm assuming so. Let's take a look. Again, this is times 10 to -7. So infrared's got to be. It's got to be infrared. I know I don't see that on that list, but that's got to be where that is, because this is the outer part of that range. This is 7 times 10 to -7 is red. Okay. All right. Let's move on. This is where. So. Frustrated because it should have been B first, then A. A better question though would have just been letter A, and not even have B, because that means you had to solve for wavelength and tell me it. So on the test, if it ever does say region, you'd be like, I don't know what it's asking for. I can't help you. You got to realize that, oh, I need to find wavelength. But letter C sometimes gets a little confusing for students. What is the energy of this radiation per photon? What you need to understand, and I wrote this on a couple of the worksheets, but it just doesn't quite click sometimes. If it says, what is the energy of this radiation per photon, I already have some information. I either have frequency here, or I have wavelength there. Energy in all of our equations is per 1 photon. That's all it is. So, when you have a choice, you should always use the value that's given to you. What I mean by that is I solved for a wavelength, but I was given a frequency. If I can use the stuff that was given to me instead of the stuff that I had to solve for, it's always a safer bet. Hope that kind of makes sense. Like, I had to solve for wavelength, I could have made a mistake. So, simply put, that's the equation would be the smartest one to go by. Reason why is that I'm using values that have not been calculated by me. But I need you to understand that when it says per photon, that is that equation. When the electron falls, a unit of energy, which we call a photon, is released. That's what this equation is. Okay? When that electron actually literally falls, photon is released of energy. So you plug that in, and you should get a value. And then I want to talk about what it means per mole. Unit, joules. So, thoughts. I believe this was in our worksheet. Not one person asked me about it. Unless I'm mixing things up right now. Could potentially be that. But it says per mole of photons. Any thoughts of what it's supposed to do? Anybody want to help me? Is it divide? Is it divide? I change your confidence that fast by just repeating what you say with a little inflection at the end? Or an eyebrow raise? You sure? What if you don't know? Let T-charts help you. What is this? This is the amount of energy per one photon, right? So what I could do is put this in here. Like you get to the test and you're just unsure. Write it out. This is per one photon. So it's asking for 1 mole. So you're going to go with divide? Okay. But it's per mole. So 1 mole is right here. So how many photons are in a mole? It's on your orange sheet. Evelyn, did I talk you out of your answer? Whoops. Oh my God. Didn't you say multiply? And then I said divide? Yeah, I couldn't remember which one. It was a whole eyebrow question mark kind of thing. That's how you do it. You feel like, wait, that doesn't make sense. I should be dividing by the number. Well, yeah, but I only have 1 photon right now. I need to know how many, if I had a mole of them. That makes sense. I need a mole of them. I only have 1. So dividing it's not going to make sense if you actually see it. You have to multiply to get to a mole. So that's going to be big. Or is it? Well, it's decent compared to what we started with. If you're doing sig figs, and you always want to keep 3, that would be how you'd have to write it. I'm not overly stressed out about it yet, but I need you to realize that if you're already feeling uncomfortable and you're writing too many digits, starting to put decimals is not a smart idea. Like I'm already putting 5 before the decimal place. Your choice of now putting 0.112 is not a good choice. You've already broken your 3 decimal or your 3 sig fig rule. So don't start adding more if you're already uncomfortable about it. Okay. So I want, wait, is that not it? Sorry, one last one. A carbon, oxygen, I want to do this without calculating. I should have written that, without calculating. A carbon-oxygen bond in a different molecule absorbs radiation with a frequency equal to that. Does this radiation give out more or less energy? So let's just relate it to frequency. So that's a lower frequency, right? So let me just think about this for a second. If I have gamma here, I want to do this without any math. As I go this way versus, like, well, let me not do it that way. Wavelength, let's do it this way. Which way does it get larger as I move? It gets bigger that way, right? So frequency gets bigger the other way. So because of that, I can figure this out. Is that frequency larger or smaller than that? Sorry. It's a little smaller, right? So It's a little smaller, so I'm further to the right because it gets larger to the left. So does that mean that it's giving off more or less energy? That's the last one we have said. Which way does energy go? Towards gamma or towards radio? Energy goes towards gamma. So it's going to be more or less energy. Less. Because energy's more this way, right? Energy's more to the left. I'm more to the right for my frequency. If I ask for non-calculation, you just say, hey, you don't get a calculator. Actually, I just pointed mine. Turned away like, well, I don't like this problem. You think about turkey and stuffing?
No.
Okay. You look tired.
I am.
Should we see if you're alive? Let me know. 93.7. You're alive. Good temperature. Here we go. Good. Anybody else wants to see their core temperature with the IR thermometer? We'll go for it. Here we go. Next one. You will be given this equation. But it says calculate the wavelength of light emitted in the spectral transition from n equals 4 to n equals 2, and the hydrogen has to be hydrogen. If it doesn't say it, assume it. Okay, so if you don't remember this, oh, I'm pulling this from my own head here. I think I'm getting this right. We're going to go with it. That's the equation. And simply, I don't even know what to say I'm testing you on. I guess I'm testing you that you understand your final versus your initial, and that you know that you should use this equation. There's not a lot else to say. So, can you execute this right? And can you plug it in correctly? I guess I will say one thing people do forget to square. It's very common, extremely common. Please show the work, put it in properly. You can, I'm going to erase the ends and just put in my numbers, but I'm going to say, I'm not going to say anything else. You have it the proper way. You're going to put the 4 and the 2 in the proper spots. What is the final calculation? See what the temperature is inside that. $110, $113. Fair. What's my final, 4 or 2? Those are the options, yes. Final is 2. It said the transition of energy level 4 to energy level 2. So I'm ending at 2, I'm starting at 4, so I'm really having 1/4 over 1/16. Make sure that you're doing that correctly. I got why is it negative? Besides the fact that there's a negative. Is the electron falling or jumping? Falling. And when it falls, it releases or absorbs energy? Releases energy. So I'm losing energy. The atom has less energy. That electron has less energy, I should say. When it jumps, it absorbs. That's why if you did that and you flipped it, the values would create a negative, which would offset the negative. And that's why it works. So that's why that negative is in place. Okay, we are shifting gears big time. I'm going to give the next couple minutes, and it's only 2 or 3 tops. Without writing them all out, you should be able to look at the location on the periodic tables, and I'm going to do one of them quickly here. It says, how many half-filled orbitals do each of the following have in the ground state? Ground state means what you would fill in if I just say, what is the electron configuration? So don't get ever confused. I can never ask you about the excited state because I have no idea where those electrons are going. There's too much information to know how much energy was put in, where the electron's actually jumping. There's way too much. The ground state. So how many orbitals, and that means the lines, literal lines, do I have half filled, meaning only one electron? So if I look at oxygen, I'm going to tell you right now the answer is 2. And the reason why, and if you want to write them out, you can. I'm just going to show you one of them, but I want you to try to do this without looking at it or without drawing it all out. You need to think about usually the valence electrons, unless if there is a d orbital, and it would look like that. That's oxygen. There are 2 unpaired electrons. Now if you're like, whoa, this is new, what are you doing? No, what it does, it shows me how well you actually understand where things are located. Okay, so I want you to compare with others. If it's 0, it's 0, by the way. Come up with it. Think about where the electrons are placed last. That's my clue to you. It's usually where the electrons are placed last. That'll be the clue of what you're going to look at. You're not looking at 1s if you're at 44, right? Come up with numbers. I'm going to pause it if you're at home. Come up with it and then hit play. Going back quickly, and we're not going to write it out. See, this is why I never got the perfect paper, because I don't read very well. It has calculate the wavelength. So when you were done, you needed to do one more step. My fault, all me. You should have then plugged it into this. So this energy then plugs into here. Okay. Maddie, did you get an answer?
Yes, I did.
What?
I got negative 4.87 times 10 to the -7.
So I'm glad you actually said that. A wavelength is never negative. Sign is just direction. Energy is in or out, but that out is the photon coming off from that electron falling. So it doesn't matter. It doesn't care that the electron lost it. It belongs to that photon. So you would never do a negative wavelength. You would never do a negative frequency. You'd be like, yeah, but it was negative. Very true. But energy is just point of view. If it's negative, that means I don't have it. That means you have it. If it's positive, you don't have it. I have it. So energy is tricky because it's all about who has it or where is it going, direction-wise, not magnitude in per se like a wavelength or a frequency, even though there's magnitude obviously. But, all right, give you about 30 more seconds on these. Okay, I do not have these written down. I'm going to do them with you. But let's just see. So, letter D, MN. What do you got? Who came up with something that they feel good about? MN. Someone. Yeah, Ash.
5.
She's awake. Why? Because it's 3D5?
Yeah.
Yep, I'm just going to write that on the side if you're like, why? 3D5. They'd all be separate. Well, what about the rest of it? Doesn't matter. It had to have been full. Like you only look at where it was filled last. Now these can be tricky because it drops a level, and that's not quote unquote a valence electron, but that's where you place it last. All right, we'll go back to. Why did I do that one next? We'll go to B. So letter B or element B. How many? Someone. 1. Seth, yes, because it's 2p1. Right. That's the. I'm just writing that as a like that's what dictated it. Okay. AR. 0? Yeah, 0. And what dictates that, is it 3 or 4? 3? It's a 3p6, so those would all be full, right? K. K would have 1, because it's 4s1. We'll skip CF for a second. Zinc. That one's a little tricky. Or not. I don't know. That'd be, it's 0. It's a 3d10. So, let's talk about CF. So CF is sitting on what? Go backwards. Don't go from the left on 89. I actually start here. So this has to be 5F14. So 14, 13, 12, 11, 10, 9. Probably want to draw that out. So that's 5F9. But I got to talk about something else too. That's 7 of them. So I go up, 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 down, down. This is a trick problem. It is not 5. Why is the answer 6? Does anybody know why the answer is 6? And it's not an exception. It's just the F block is funky. Unfortunately, I'm slightly covering it up potentially based on the periodic table. Why did I say count from the right? If you count, anybody want to, how many are in this row? Anybody count that? It's not 14. It's 15. What are these first 2? The LA and the AC, they actually belong in this section. So, this is where it gets weird. And I don't feel like this shatters your idea of chemistry. There's a 6D1 that's sitting there that you enter the D, you go to the F, and then you come back. It only is if you stop in the Fs. Why we don't talk about this much is that you hardly ever stop in the Fs, because you don't deal with things in the Fs. You just don't. It's not going to be some weird thing on the test. I'm not going to try to trick you at all, but you do need to understand that that is what actually happens. So I just want to see it. If you got to the 5F9, I feel great. For now. Okay? But just understand that it's weird. It just happens. Okay? So there we go. Let's move on. In which orbital would an electron have a greater likelihood of being near the nucleus? So quick answer. Now, this could be a free response question as well, but I just want you to come up with an answer and a very short idea of why, or you could give it to me in less than a sentence of just what it is. So if you haven't started on this, I'll give you 30 seconds. Just which one would be the likelihood of being most near the nucleus? Give you a second. If you look at the energy level only, it could trick you. The cheat pyramid that we learned a long time ago is the periodic table. And if you start filling in the periodic table starting at 1s and you just go through the blocks, what am I doing? I'm putting the electrons in order of lowest energy. So the simplest answer I can always give you, and I don't have this memorized, and I might just by accident, is I know the lowest energy to the next is also linked, first off, to the distance from the nucleus. Because as you have to get further away, you have to gain more energy. And the order of the periodic table tells me that. That's all I need to know. So which one comes first, the 6s or the 4f, if I'm filling things in? It's a 6f, and obviously if you're watching this at home, you can't see this with us. But 6s, after you go to 6s, technically you go to a 5d1, and then you drop to where we just were. Actually, we're at a different one, but 4f. 4f is in the block, then it comes back. I could have asked a bunch of questions. So first off, this is the answer because it has lower energy, because the electrons actually fill it in first. But here's one that was here. Which one's filled in first? The 4s, isn't it? Like if you're why I'm bringing this up is that this is something you can talk about. Let's just talk about this one for a second. Shielding. Technically, you'd have, like, I know it's not like this. There's not a track. But if you were having electrons at, like, nucleus is down here, electrons at 4s, the 3d would be a little bit further away, and then the 4p would be a little bit further away. And that's the order that it's filled in on the periodic table. Evan?
Oh, God.
Just excited. Yeah! Nuclear distance of outer electrons. Woo! Okay. Embarrassing for you, Evelyn. Embarrassing. Does that make sense, though? I don't memorize it. It's the order, which I like. And I hope that resonates with you. All right. I'm going to give you a moment now to work on your own again or with someone else. I want noble gas configurations of these 6. Noble gas configurations by only using the periodic table. Go. Okay, let's talk about it. So, Previous row, no matter what. If you're finishing up, I'm probably not going to catch you. So slow down. Make sure you are located where you need to be. So calcium, for example, is on the 4th row, so I need the noble gas of the 3rd row. So I need argon. And then I move from there. So argon's worth 18. I need to get to 20. That's only worth 2 more. So I hope that you did that. Okay? Tomorrow, a few of you will do this, no matter what I say. Br minus has what? 36 or 34 electrons. It normally has 35. So we have 36 electrons. Number 36 is krypton, and some people do this. And they feel so good when I don't know how you don't feel weird. Or you can't be like, yeah! Why didn't he think of that before? We never did that once, but I'm going to go with it. You're on the fourth row. The rule still applies. You have to take the previous row. Even if you're a noble gas, you cannot be on it. So that is still argon. And now you do everything that's on the 4th row. That's all. So it's 4s2, 3d10, 4p6. So that's what that one should be. It does not matter the order. I like to do the order that's on the periodic table. It just makes sense to me. It gives me confidence. I'm just moving forward. I don't need to rearrange. I'm okay. Okay. Silver. I'll do the hard part. I'm being sarcastic. Who wants to give me the rest? Ashley.
5s1, 4d10.
What? Why'd you do that?
Because that's the exception.
That's an exception. It's a D9. If you wrote 5s2, 4d9, you will lose a point. D4s and D9s are exceptions. So the S1 to D5, or the S1 becomes a D10, depending on where you end. So very good. Good job. Mg2 plus. What noble gas am I using? Mg2 plus.
Or wait, that's
He. It acts like neon, but I can't use that, right? Okay. So then it would be 2s2, 2p6. Okay. We'll skip OS for a second. We'll go to nickel. And I didn't do a lot of variations here. I probably should have done a little bit more, but I just wanted some differences. So nickel, you should have done 4s2. Do the time here. 3d what? 8. Looks right to me. We only covered this quickly. Which one? I just want to quickly ask this before we get into here. Which one of these right now would be attracted in a magnetic field? Do you remember? So this ends like this with the P's. This ends with the D's. We did this right at the ending. Which one, but this was on a homework question, like which one is attracted in a magnetic field? The one that has all the paired or unpaired electrons? Unpaired. Unpaired. They're not evened out, they're not balanced out, so I have a unfortunate net in polarity, moving one way or the other. The magnets have poles. So this one would be magnetic. Or it could get trapped in a magnetic field. It's not the charge. It is not the charge. That's what people will get you with. They'll use one with a charge and use one without the charge, and they'll get everybody to say the one with the charge. Because they're like, hey, it has a charge. It must be attracted in a magnetic field. Charge has to deal with losing electrons, and now it's attracted to another opposite charged ion in a solution. It has nothing to do with magnetic field. So, just a little extra. Any unpaired electron causes it. Now, if it had more unpaired, it would be more attracted in a magnetic field. If it has less unpaired, it's less. So then going back to that last problem, or 2 problems ago before we get in there, CF would be the one that would be the most attracted in a magnetic field, because it has the most unpaired electrons. Okay? So, who is confident or want to just take a stab at OS? Okay, Joe, I just heard noises. Go. What?
Xenon.
Oh, xenon. Okay.
And then 6s2,
If you had 5d5, I get it. But if you add that up, you guys, xenon's worth 54, then you got to add 2 plus 14, and if you did 5, you would have gotten 75. Again, at home you won't be able to see this, but this right here is D1. D1, D2, D3, 4, 5, 6. Because that's the beginning of the B block. Unfortunately, on this periodic table on the wall, okay, they have LA and AC on the bottom, but on your orange sheets, they have it where they should be. Okay, so yes, that is correct. You can always double check it by adding them up. All right, last problem. We're doing great on time. Okay, you will have a photoelectron spectroscopy photo, at least one. Sometimes they have lines. They have lines that helps. Oh no, I'm supposed to see. Stop looking. At home, no one saw me covering that right now. They just saw. Okay, so there'll be lines here to help you gauge like the amount, so you would be able to know the height of the peak. But sometimes it's just about estimating. So if you feel like that's really hard or impossible, usually it's pretty obvious. So first, identify the following atom based on photoelectron spectroscopy. What is the location? Well, let's just talk about that first. So, do we know what this is? So you have to kind of figure out based on the relative amounts of electrons and the binding energy what atom this is. Okay, I'm not going to say anything else. Can you figure that out? And then, if you can, what is the location? And what I mean by that, what's the electron configuration for the electron with the binding energy of 1.31? So, like for example, is that a 4F4? Is that a 2P1? Like, what is that peak? Do you know what that peak is worth? Like, what is it exactly? And if you don't know, we'll go over this. So I'll give you about a minute. There's not much. I mean, either you know how to do this or you don't again. I would definitely look at our notes. I'll just pause it, but give it a shot. If you don't know which one to start with, you've got to understand it's based on binding energy. What does that mean? Binding energy is how strong those electrons are being bound to the nucleus. So I have a peak that's at 52.6. I have a peak, the scale got too big. So I have another peak that's at 3.04, and I have another peak that's at 1.31. Your job is to find your 1s2. It's as simple as that. Where is your 1s2? Once you know that, everything matters. Why? What that does is it tells me the peak of a 2, like how high, right? What's the distance of a 2? You know, like what's that distance? And then it also helps me with the energy. The energy is how you do it. So which one? At the 52.6, the 3 or the 1? Where's my 1s2? Is it the 52.6? Is it the 3.04? Is it the 1.31? 52.6. This is bound the tightest. This is the biggest energy. Strongest attraction. That means closest. So automatically, this must be my 1s2. It helps to write it there. Now, sometimes it will literally tell you it's a 2. I got rid of that. So that means this height is 2. So like this is 1, this is 2. It gives you a guide. So now, you just got to think, electrons fill in. So this peak must be 2s2. And it actually is a 2. So this is the one that's going to help you. How high is that one? Is that double? Is it 1 more? It's not 2, clearly, right? It's higher than that. Is it 6? I don't think it's 6. Reason why? It's 4. Good. Maybe you saw it already, but if you didn't. So what does that mean? This is, what is that peak then? 2p. What atom is this? Oxygen. And the reason why is it's 1s2, 2s2, 2p4. So this is oxygen. Okay? So that's how you use photoelectron spectroscopy. Is it gives you the relative heights. You got to find the 1s2. I think that's the key. You find 1s2, everything else. It gives you the guidance of the heights. It gives you idea of what's next. So on and so forth. So good luck.